Okay, welcome back. We will continue the discussions on the existence and uniqueness of solutions of initial value problem. Existence and uniqueness of solution of initial value problem. In the previous lecture, we have seen several examples of initial value problems. Some are having infinitely many solutions and some are having no solutions and others having infinitely many solutions. So, now we will characterize under what condition an initial value problem will have unique solution, like the problem posed by Hadamard. Once an initial value problem is given, under what condition the system has a solution and under what condition the solution is unique, and conditions for which the solution continuously varying with respect to the initial condition. So, consider the initial value problem. Given by the first order differential equation dy by dx is equal to f of x comma y, with the initial condition y at x0 is y0. So, f is a function. So, here f is a function which is defined on a domain D, a subset of D which is a subset of R2 to R, is a function of two variables as it is defined on R2. F is a function of two variables x and y. With respect to the initial value problem, the first argument x, that is a independent variable, and y is a dependent variable which is of course the solution we are looking for. So, f is defined on a domain D. So, D is a domain in R2. By domain we mean D is an open set in R2 and also it is connected. It is a connected set. Any two given points in D that can be joined by a continuous curve which is completely inside D. So, D is a domain in R2. So, our initial value problem given by dy by dx is equal to f of x y and y at x0 is y0. So, you have this is your x axis and this is your y axis and a point. So, this point is x0, this point is y0. So, initial point is x0 y0. We are looking for a function starting from this point. and f is defined on the domain D, and to make sure that first of all the solution, the initial value problem has a solution, we require certain conditions on f. So, let me first state the conditions, we will do the proof later. So, for excisions so if f of x y is continuous on D, then there exists a solution y of x to the initial value problem in some neighborhood, in some interval, say x 0 to x 0 plus h. So, we will prove this excisions results later. So, broadly speaking, if f is continuous in the given domain, the domain contains initial point x 0 y 0, then one can show that there exists a solution at least in some neighborhood that contains the initial point x 0 y 0. Now, uniqueness problem. So, if f x y is Lipschitz continuous with respect to the second argument, y, on the domain D, then the initial value problem has a unique solution. Rather, the solution of the initial value problem is unique if solution exists. And if x y is Lipschitz continuous with respect to the second argument, that is y, then the solution is unique. And the third problem is stability. So, if f of x y is continuous with respect to x and Lipschitz continuous with respect to y, then the solution of the initial value problem varies continuously with respect to the initial condition. y 0. So, these are the three major solution to the Hadamard problem. So, we will address each one of them separately and we will give sufficient proofs for each of them. See, in the existence problem, what we require is the continuity of f with respect to both x and y, continuous with respect to x and y. Okay. So, because f is defined on the domain D, which is a subset of R2, which, okay. If f is continuous with respect to x and y, then we can show that there exists a solution in some neighborhood containing the initial point x 0 y 0. And the second problem, uniqueness is guaranteed if f is Lipschitz continuous with respect to the second argument y, and of course, continuity is required for the existence of a solution. So, continuity is also required for the existence of solution, and uniqueness is guaranteed if f is Lipschitz continuous with respect to the second argument. Okay. And the stability, the continuous dependence of the solution on the initial condition y 0 is also guaranteed if f is Lipschitz continuous with respect to y and continuous with respect to x. And we will show it, and for Lipschitz continuity we have already seen the definition and examples of a Lipschitz continuous function in the preliminaries. There we treated a function of a single variable, a function of x only, f of x, and also we have seen sufficient conditions under which a function is Lipschitz continuous, and examples of Lipschitz continuous functions and examples of functions which are not Lipschitz continuous. Now, since we deal with the functions of two variables x and y, we will briefly deal with the Lipschitz continuity of f with respect to the second argument y. Okay, definition. So, definition 1, let f x y be a function which is defined on D, which is a subset of R2 xy plane and is mapping to R. Let be a function, okay, not necessarily linear, so could be a linear or nonlinear function. Now, f is said to be Lipschitz continuous with respect to y if there exists a constant, call it alpha greater than 0, such that f of x y 1 minus f of x y 2, the absolute value of this is less than or equal to alpha times y 1 minus y 2 for all x y 1 and x y 2, x y 1 comma x y 2 are in the domain D. And if there exists a constant alpha of satisfying this condition, you take the least of all such alphas and we call that alpha as a Lipschitz constant. So, alpha is a Lipschitz constant. Constant of f with respect to the argument y. Now, as in the single variable case, if D is the all space R2, if D is the entire space R2, then we say that f is globally Lipschitz continuous, globally Lipschitz with respect to y, otherwise locally Lipschitz. For existence and uniqueness, for uniqueness result, when a local Lipschitz continuity is sufficient. Now, let us see an example. So, example say 1. So, consider a function f x y which is given by x plus 3y, where x and y they are on the entire x y is on the entire R2. So, let us check the Lipschitz continuity of f. So, f of x y1 with respect to y, f x comma y2 which is x plus 3 y1 minus x plus 3 y2. Okay, so which is equal to 3 y1 minus 3 y2, 3 times y1 minus y2. So, therefore, modulus of x y1 minus f x y2 is equal to 3 times y1 minus y2 for all x y1 and x y2 in R2. So, this shows that f is Lipschitz with a Lipschitz constant 3. So, therefore, this function f given by f is equal to x plus 3y is Lipschitz with constant Lipschitz constant alpha is equal to 3. And this Lipschitz continuity is global because it is true for all points x y1 and x y2. So, therefore, f is globally Lipschitz with respect to y. Now, consider another example. So, consider the function of two variables x and y given by x square plus y square. So, these two variable functions. So, let us check the Lipschitz continuity. So, f of x y1 the first point and f of x y2 the second point. These 2 points are arbitrary points in the xy plane, that is in R2, which is equal to x square plus y1 square minus x square plus y2 square. So which is equal to y1 square minus y2 square, which is expanded as y1 plus y2 into y1 minus y2. So therefore f of x y1 minus f of x y2 is equal to if is less than or equal to y1 plus y2, if we can bound, times y1 minus y2. So we know that this quantity y1 plus y2, as long as these points are arbitrarily varying in the all R2, is not bounded. For all x y1 and x y2. Of course, if y is bounded, the y coordinate is bounded, then this quantity can be bound by a constant. So for example, if you take an infinite strip, this is x axis and this is y axis. If I vary y between say minus b and b, and if I take this infinite strip, so if I call this as D, so D is set of all x y in R2 such that x is varying from minus infinity to plus infinity and y is varying from minus b to plus b. So on this D, the given function, since y1 plus y2 is bounded by 2b. Okay. So now y1 plus y2 is less than or equal to 2b on D. So therefore we conclude that this function, the function given by f(x) is equal to x square plus y square, is Lipschitz continuous if Lipschitz with respect to y with the constant, the Lipschitz constant alpha is equal to 2b. So a function of two variables x and y, and we have verified the Lipschitz continuity, and this Lipschitz continuity is local. Okay. So this is Lipschitz continuous and this function is Lipschitz, and the Lipschitz continuity is local. So this is locally Lipschitz with respect to y, and that is on the domain we just defined D. So on the domain defined by this set x of set of all x y such that x is varying from minus infinity to plus infinity and b is varying from minus b to plus b, is an infinite strip parallel to x axis. And we now see a function which is not Lipschitz. So example of a non-Lipschitzian function. So example 3. So consider a function f of x y a function of two variables which is given by x into square root of y. So, x into square root of y, and suppose that this is defined on a domain where x varies from 0 to 1 and y varies from 0 to 1. Okay, so the domain you are looking for, domain is set of all x y in R2 such that x is varying from 0 to 1 and y is also varying from 0 to 1. So, this is your domain. Now, let us check the Lipschitz continuity of this function on this domain. Okay. So, let us compute f of x y1 minus f of x y2. Now, we are looking for a condition like this, f of x y1 minus f of x y2, value of this one is less than or equal to alpha times y1 minus y2 for all x y1 in D and x y2 also in D for all points x y1 and x y2 in D. We show that it is not possible for this function to have a condition like this. So, this is a question mark whether this condition is satisfied or not for any arbitrary point x y1 and x y2. Let us take 2 points x y1 I am taking as 1 0 or okay, 1 y arbitrary y and x y2 let us take that as 1 0. Okay, 1 y where y is a value. So, where y varies between 0 and 1, y could be any value between 0 and 1, and x2 or y2 is a 0 and x is 1. In both points the x coordinates are 1 y and 1 0. Let us compute so therefore f of 1 y minus f of 1 0, this is equal to f of 1 y by definition of your function. So, x is 1 and this is square root of y minus f of 1 0. So, y coordinate is 0, this is 0. So, this is equal to square root of y and y is positive. So, this I write as y is 1 by square root of y times this is so times y minus 0. So, if we can bound this quantity by a constant finite number, okay, alpha, then it satisfies Lipschitz condition for this point, and we know that as y is approaching to 0 from right side of course, the quantity 1 by square root of y, it goes to infinity, okay, showing that there does not exist an alpha, okay, satisfying a finite number alpha positive satisfying the condition. If I call this condition as star, satisfying star. So, as y approaches to 0, as this is x axis and this is y axis, as y approaches to 0, then this quantity 1 upon square root of y, that blows up. So, therefore, Lipschitz condition is not possible. So, the conclusion is the function f x y given by x square root of y is not Lipschitz on the given domain D. So, therefore, this function is not Lipschitz continuous, even not even locally Lipschitz continuous on D. So, therefore, always to check Lipschitz continuity by this method may not be that very straightforward. Now, as in the case of one variable, there are sufficient conditions which ensure the Lipschitz continuity of a function of two variables. So, now I will state a theorem that ensures or guarantees the Lipschitz continuity of a function of two variables with respect to y. So, theorem, so say sufficient condition to guarantee Lipschitz continuity of f, which is a function of two variable with respect to the second variable y. So, we deal with sufficient conditions. So, we state this in the form of a theorem. So, theorem 1, let D be a closed domain in R2. So, that is a domain is it's a connected set, an open connected set which is also closed. So, we look for a closed domain in R2 such that the line joining any points in D lies entirely within D. So, we take a domain, a closed domain such that any 2 points, the line joining them should lie completely inside D. Suppose that the supremum suppose that okay, f x y, suppose that f x y is differentiable with respect to y, and the supremum of the partial derivative del f by del y the supremum of the absolute value of the partial derivative of f with respect to y, where x and y lies in the domain D, the supremum is attained, and which is equal to alpha is a finite number. If the partial derivatives are now bounded in this sense, then the conclusion of the theorem is then f of x y, which is from, of course, from D to R, is Lipschitz continuous, with respect to the second argument, with respect to y on the domain D with the Lipschitz constant alpha. So, the sufficient condition that guarantees the Lipschitz continuity of a function f is that, so function f x y, if f is differentiable with respect to the second argument y, and if the partial derivatives with respect to y is bounded, or supremum of the absolute value of the partial derivative is a finite number in the domain, then the function f itself is Lipschitz with respect to y. The proof is very simple. I will just give the proof. The proof is just by using the mean value theorem. So, let x1 xy1 and xy2 to be 2 points in D. Let xy1 and xy2 be 2 points in D. Now, by Lagrange mean value theorem, by the mean value theorem, we have, there exists a number psi between y1 and y2 such that f of x y1 minus f of x y2 is equal to y1 minus y2 times del f by del y at the point x psi. So, this psi is a point between y1 and y2 that is guaranteed, that is assured, because we assume that in the domain D the line joining any 2 points that lies entirely inside. So, therefore, psi is a point between y1 and y2 which is totally inside the domain D. Now, taking the absolute value, so this implies the absolute value of f of x y1 minus f of x y2, which is obviously less than or equal to supremum of del f by del y at x I times y1 minus y2 for all x y1 and x y2 inside T. And by hypothesis, this is bounded by, okay, this is alpha. So, this is less than or equal to alpha times y1 minus y2, okay, for all x y1 and x y2 in D. So, proving that f x y is Lipschitz with respect to y with the Lipschitz constant alpha. So, therefore, if a function is differentiable, it is easy to check the Lipschitz continuity if we can find the bound for a partial derivative with respect to y. So, let us take the example, a similar example which we considered, example 3. So, let f of x y is equal to x plus y square, where x varies from minus infinity to plus infinity and y is bounded by b. So, absolute value of y is less than or equal to b. So, obviously del f by del y, the partial derivative of f with respect to y is 2y, and del f by del y is equal to 2i is equal to 2 times y, and y is bounded by b. So, therefore, this is less than or equal to 2 times b. So, this shows, so this implies that f of x y given by x plus y square is Lipschitz on, okay, if we say this is a domain, if domain D is given by this on the domain D with alpha is equal to 2b. And at this junction, we know that this the conditions in the theorem is not a necessary condition to for a Lipschitz continuity. It is just a sufficient condition. If the partial derivatives are bounded, then the function is Lipschitz continuous. That is a strong sufficient condition. But there are functions which are Lipschitz continuous, but at the same time not satisfying the hypothesis of the above theorem. So, we give a counter example. So, example. So, consider a function f of x y is given by x into absolute value of y, where the domain is, which is defined on a domain where x y such that mod of x is less than or equal to a and y is between minus infinity plus infinity. It is also an infinite strip where y varies. So, from minus infinity to plus infinity, x is bounded between minus a to a. So, this is so this is the domain. So, if you check for a Lipschitz continuity, f of x y1 minus f of x y2, where x y1 and x y2 are 2 points in the domain, which is equal to x absolute value of y1 minus x absolute value of y2. And if we take the absolute value of this, so this is less than or equal to mod of x into absolute value of y1 minus y2. And as x is bounded by a, so this is a times absolute value of y1 minus y2. So this shows that the function f given by x into mod y is Lipschitz with the Lipschitz constant alpha is equal to a. However, this function does not have a partial derivative with respect to y, as it is not differentiable with respect to y at 0. So therefore, the conditions in the theorem is just necessary, just sufficient. So the conclusion, the condition in the theorem is just sufficient. But not necessary to guarantee Lipschitz condition. Lipschitz continuity of f with respect to y. So therefore, a given differential equation, we can check the continuity of f with respect to x and y, and also check the Lipschitz continuity of f with respect to y to address the question of existence, uniqueness, and continuous dependence of the solution with respect to the initial condition. And also note that Lipschitz continuity is a stronger notion than continuity. Any Lipschitz continuous function is continuous, but lit less than the differentiability. For proving the uniqueness result, we employ a very important lemma, which is known as Gronwall's lemma. Gronwall's lemma. So this will be invoked to prove the uniqueness of solution of an initial value problem. So let me state the Gronwall's lemma. Suppose that fx and gx are continuous real valued functions so continuous real valued functions with a condition that f of x is greater than or equal to 0 and g of x is also greater than or equal to 0 on an interval, call it a b. So if fx and gx are two continuous real valued functions, both non-negative and defined on an interval a b, then if we have an inequality, that is f(x) is less than or equal to some constant c plus k times integral a to x gs fs ds, where c and k are no negative constants. Then the conclusion is f of x is less than or equal to c times exponential integral a to x gs ds. So, this inequality is known as a Gronwall's inequality. If f(x) is less than or equal to c plus k times integral a to x gs fs ds, then f(x) has to be bounded by f(x) is less than or equal to c times e to the power integral a to x gx ds. In the first inequality, f(x) is there on both sides, left hand side and the right hand side, and the conclusion is f(x) can, if this is the case, then f(x) can be bounded by a function which is independent of f. The proof of this inequality is, so what we have is, we have f(x) is less than or equal to c plus k times integral a to x gs fs ds. This we have. And if I take the RHS and denote this by gx, so let gx is equal to c plus k integral a to x gs fs ds. So, this implies that, so thus what we have is f of x is less than or equal to gx by definition. It is a hypothesis, because gx is your RHS. So, f of x is less than or equal to gx. And also g of a, if you evaluate g at a, integral a to a, which is 0, which is just c. And if you differentiate g prime x is equal to, if use Leibniz formula and differentiate this integral, so first part is 0, then k times, this is k times gx fx. So, therefore, g prime x is, so therefore, we get g prime x is equal to k gx fx, and this fx is less than or equal to gx. So, this implies that this is less than or equal to k times gx capital Gx. Okay. In other words, what we have is g prime x is less than or equal to k small gx into capital Gx, and if you divide this by gx, so g prime x divided by gx is less than or equal to k small gx. Now, integrating this, integrating over the interval Ax, we have that integral of g prime x by, which is g prime, so call it gs by g of s ds, integral a to x is less than or equal to integral a to x k times g of s ds. By using the integral of derivative by the function, which is nothing but the logarithm ln of GS and evaluated at these 2 points a and x is less than or equal to integral of a to x k GS ds. So, since g of s at a is c, this is ln of gx divided by c less than or equal to integral a to x k GS ds. And taking exponential on both sides, you get gx is less than or equal to c times e to the power integral a to x k GS ds. And from our hypothesis, we know that fx is less than or equal to, we know that fx is less than or equal to gx. So, therefore, fx is, so this implies fx is less than or equal to c times exponential integral a to x k GS ds. So, this proves a Gronwall's inequality. And as a remark, in the Gronwall's inequality, I can say as a corollary, see as a corollary in the Gronwall's inequality, if c is equal to 0 in Gronwall's inequality, then f of x is less than or equal to k times integral a to x GS fs is ds. This implies that f of x is equal to 0. So, that proof follows very easily, because if we take for every epsilon, we take an epsilon greater, for every epsilon greater than 0, the Gronwall's inequality holds, and if that holds, then you get epsilon times k integral a to x GS fs. So, that makes that fx to be 0, since fx is non-negative. So, this result we will be using in proving the uniqueness result, the Gronwall's inequality. Okay, now we have built up necessary tools to prove the uniqueness of an initial value problem if the function f is Lipschitz continuous with respect to y. So, that the uniqueness will be proved in the next theorem. Okay, so, therefore, two things we have seen, that one is if the function is continuous with respect to x and y, then there exists a solution to the initial value problem. If the function is Lipschitz with respect to y, then the solution is unique, and continuous dependence will be shown later. Okay, we will see the proof of this in the subsequent lectures. Okay, bye.